Yeah? All right, hello everyone. Thank you for attending my closing keynote on scaling blockchains and DApps. So some of you already know this joke. I got assigned the very last speaking slot, and as my revenge, I'm calling it the closing keynote. And this is how I've been advertising it. So yeah, if you're anything like me, by now you cannot distinguish between your jet lag and sleep deprivation anymore. So I won't go into the math of zero knowledge proofs and instead just talk about the general challenges of scaling blockchain. Let's start with, so again, I'm Remco, I work for zerox.org. So zerox.org is a decentralized exchange protocol. What we're trying to work towards is create a tokenized world where all value can flow freely. With this, we mean that just in the way that the internet democratized the access to information, we believe that blockchain technology will democratize the access to all sorts of tradable assets, and we want to build the equivalent of HTTP and SMTP to make this happen. So we focus on developing the core protocols to allow this smooth and liquid trading of assets. And we do this according to 3 principles. Do the right thing, consistently ship, and focus on long-term impact. I would say this deck is very much about long-term impact because scaling. So I joined ZeroX. Actually, I was one of their security auditors way back already, but I joined them full-time a little over a year ago. And my basic mandate there can be summarized as make sure ZeroX runs on the best technology. Now, I've thought about this, what this exactly means. It means that help out the technology projects that we currently build on. It also means pick promising new technologies that we should be building on. And it means sabotaging projects that we don't build on. Wait, this doesn't align with our values. No. I also help out other projects that might potentially be interesting to us. And this is something I want to emphasize a little bit more. What is so unique and wonderful about the Ethereum space right now is that you have this ability to relatively freely and unconstrainedly work with some of the best and brightest minds in the crypto industry. And honestly, I cannot stress enough how unique it is. There's a very decent chance that this will only last a couple more years, and we should really enjoy this opportunity to work with each other, not against each other, and work with each other towards these common ideals of decentralization and open source. This is like our one shot at proving this at scale, and we should take it and make it work. Now, speaking about grand challenges, I think the main bottleneck right now is scaling. Now, why scaling? Very simple. Right now, we have more developers than users. Like the developer to user ratio of Ethereum right now is unlike any other technology out there. But we cannot really handle volume of users yet. And you may think that, well, let's wait for the users to come on first and then we'll deal with the load as it comes. But this is honestly not how it works. If you look at what happened, for example, with IBM Maersk and their logistics blockchain, or other really interesting applications of blockchain that we've been rallying about pretty much since Ethereum and the smart contract idea launched, you will see that a lot of them are now running on private chains. And most of them do that not because they fundamentally hate public chains. They do it because they cannot guarantee their stakeholders that they will hit their performance targets on the current chain. So, yeah, a lot of new use cases like gaming, logistics, even prediction markets, they don't really will run that well at scale on the current current infrastructure. So that needs to be addressed. The other thing is that, specifically for ZeroX and the exchange market, like right now, DEXs don't have that much of a transaction volume. If we take market share from crypto exchanges, this will grow. If we take on security tokens, this will grow even further as we take on the transaction volumes of traditional exchanges. if you get to more of a consumer end, where we're going with this tokenized world, you will rather be comparing yourselves to the volumes that the Visa network handles. And actually the reality is that we're shooting for way more than that. We're shooting for a world where every single in-game asset that you're handling will be tradable in some form of a decentralized system. So the actual volumes that we should be targeting for over a longer term horizon are way, way larger than anything out there right now. So what does this mean for scaling blockchains? Now, scaling blockchains is not a new idea at all. Pretty much as soon as Bitcoin launched, it was clear that it needs to scale in order to get widespread adoption. Ethereum is no different, and people have been thinking long and hard about this problem already. The general consensus around scaling right now is that we need a twofold strategy called Layer 1 and Layer 2. Layer 1 means scale the basic infrastructure, scale the underlying blockchain. There's a couple of really promising projects out there. Not all of them are on this slide for sure. And I will go into the details of like the various trade-offs that they're making here later. The second is the Layer 2. So okay, let's accept the fact that Layer 1 has limitations. How can we still build applications on top of it? And you can actually get some additional scaling benefits by taking this separation into account. The reason is that in most applications you have domain-specific knowledge, you can make domain-specific security trade-offs, and the whole equation becomes a little bit easier to solve. So you end up with next-level scaling solutions that can actually take the whole thing way further. At 0x, I'm very much researching this area in the context of decentralized exchanges. We'll get into that later. First, I want to talk a little bit about Layer 1 scaling. Now, Layer 1 scaling means a number of technologies. This is far from exhaustive or comprehensive, but in orange you will see the first one is sharding. So instead of having every single node of the network re-evaluate every single transaction, we sort of figure out a way to securely divide up the work among all the nodes that are live and have everyone do some fragment of the total amount of work, and basically combined we will do more than each of us could be doing individually while still retaining security. This approach has a problem that you have these different environments that need to communicate with each other. So you end up with systems that are fundamentally asynchronous. We'll get into the implications of that later. Another big thing that Ethereum is likely to do in some future is called pruning. Right now, Ethereum keeps the entire state and history of every single transaction along on every full node. In principle, this is not necessary, because in Ethereum, in order to securely know what the latest state is, all you really need is the latest block, the state that is attached to the latest block, and the chain going back to the Genesis block. But you don't need historical transactions, because unlike Bitcoin, Ethereum uses this state-based model, where basically the latest block always contains all the information you need to know in order to make progress in this system. Yet we haven't really implemented that yet. At this point, we still store all of this data around transactions there. So one of the things we can do is get rid of that. Some other things, proof of stake, Casper, they have more to do about how you reach consensus, how you get rid of like this mining overhead. State rent is another interesting one for DApp developers. The gas model needs to accurately reflect the underlying cost of the blockchain, of operating it, and any kind of discrepancy in there can lead to problems over time as this discrepancy escalates. One of the things we've really seen escalating is the cost of storage, because right now in Ethereum you pay a one-time fee to have your information stored forever, and since we don't have sharding yet, also on every single node. This cost obviously does not make a lot of sense. So this is why state rent proposals are out there, where instead of a one-time fee, you would have to incur an ongoing gas fee to to keep your storage in a contract. This has very far-going implications for how we currently develop DApp, so I'll get into that in a moment. Another trend seems to be looking into WASM as an alternative to EVM. WASM has the advantage that it's a little bit of a closer match to the underlying CPUs, and it has way more developer resources allocated to it by virtue of it being the standard in browsers. Not all of that is entirely applicable in blockchain because the security model is slightly different, but there seems to be some consensus that the future will be WASM based. At least this is what ETH2X, Dfinity and Polkadot are shooting for, as far as I understand them. Then another development is to rely a little bit more on light client protocols so that we can have beefier machines do the full node stuff, but still be able to give hard security guarantees to people who cannot afford to run beefy servers. And you can actually use zero-knowledge proofs on the layer 1 level to do scaling. So instead of what happens now when you've mined a new block, you send it to the network, and then all the nodes on the network recompute the entire block and all its transactions in it to verify it. Instead of that, you could imagine computing a zero-knowledge proof that proves that this is a correct block and this state update is correct. And then all the other nodes will only have to verify a tiny little proof. This is a very promising approach, but as we will see later, zero-knowledge proofs are still relatively immature, so this is not within the realm of feasibility soonish. That being said, there's a project called Coda Protocol that is already experimenting with this technology to do blockchain scaling. Now, what do all these planned changes and necessary changes mean for DApp developers? It basically means that the future will be WebAssembly, asynchronous, and state rent. And this in turn means that if you have a contract that currently does a mapping from address to something, this will likely not work. Because this means that your contract has to store data for every single user, which means that if I create 1 million fake accounts, store some data in your contract, and then disappear from the network, you will end up paying state rent for all my data in eternity, which you don't want to do. So that doesn't scale. You want to come up with better solutions there. Same with transfer from, as we do it now, where when the call returns, you know that the funds have been successfully received and all that. This doesn't work in an asynchronous world, and as far as I know, we don't really know yet how to handle tokens in an asynchronous world. This is somewhat of an open research question. Another a little bit more technical issue is applications that for their security depend on storing data in log messages. If we get to pruning of state, then eventually these log messages will not be available anymore. So you would maybe only have access to, let's say, the last year or the last 3 years worth of log messages. If this breaks your application, then you need to reconsider how you're using these log messages. And one thing I'm fairly confident of is that no feasible long-term scaling future will contain anything close to ERC20 because it pretty much breaks all of these 3 concerns. This means we need to rethink how we're doing this whole ecosystem. And one thing that's kind of surprised me in engaging in these conversations about all these different scaling proposals is how underrepresented the major DApp developers are. I really urge the people that are working on large projects that have a big stake in the Ethereum ecosystem, that know what is going on, that understand the technology deeply, to talk to their core devs or at least attend the ETH Magicians meetings, listen in on the changes, think about what these changes mean for your DApp, and maybe even give some ideas on, hey, if you do this and this way, you would scale and it would help us. Don't bother them too much, though. They're also quite busy, and they're doing great work. In general, they do know what is going on, but yeah, get involved. make sure you have a scaling strategy in your organization. Now this sounds maybe a little bit glim, so I want to give a little glimmer of hope in there. This is like a random idea. I was originally planning to do at ETH Denver as a hackathon project, but ended up not being able to go there. So I'm just throwing it out there for anyone to do at ETH Paris if they feel like it. It's a shard token. It is a token that is fully shardable and doesn't maintain state per user. So it would basically work in this future scenario. And it works right now on EVM, on our current EVM. The basic idea is that, getting a little bit technical here, but the basic idea is that you have this create opcode, not even create2, the original create will also work, and it gives you a predictable address. If some contract creates a new contract, the address will be predictable, which means that if you, it's basically a hash of the current address and a nonce. Now, if you have this nonce, you can prove that this contract was created by another contract. If you have a chain of these nonces, you can prove that this contract was descendant from a common ancestor. Now, if my contract knows its own ancestry proof, it can pass this along to another contract and prove to that contract that they are cousins, that they are both descendants from the same ancestor contract. Now, with this funny little primitive, you can create a minting contract and then have it spawn different wallet contracts. And each wallet holds a balance for some user. And now when a user wants to transfer, they can give the address of the recipient contract, and the shard token contract will call the receive function on the other wallet, and the receive function will verify that, yes, we are indeed in the same family of token, so I can accept your balance because this cannot be minted or double spent or a fake contract that pretends to be family. Like, you can prove that contracts are in the same family securely. And the funny thing is, you don't ever have to call the original minting contract again. So this is what makes it shardable and sort of state rent secure. Everyone just pays for their own wallet, and the wallets can transfer funds directly to each other without having to go to a centralized ERC20 token contract. Anyway, fun thing out there. I hope someone picks it up. So that's it for layer 1 scaling. Let's move to layer 2 scaling. So this is sort of scaling strategies that you as a DApp developer can use right now, right away, to make your DApp better. I like to put them in like sort of 4 quadrants. There's basically 2 overall strategies that you can take here. You can either put your data on chain, or you can decide, I'm not going to store everything in storage. I'm going to leave some of it in some secondary system. And another strategy you can do is how do you prove your state transitions in your DApp? And you can do an honest proof approach, where whatever you're submitting to the blockchain is always a full proof that whatever happened was entirely according to the rules of your DApp. Or you can move to a fraud proof approach, where you basically say, well, here is the update, trust me, and if you don't believe it, tell me and I will send more proof. Let's go over the basic approaches here. So when it comes to storing data on-chain, like, there's not much you can do really in this area. You can do gas golving to get the transaction cost down, basically just optimizing your EVM code. You can invent some clever compression algorithms to reduce the cost of your transaction data. You're fairly limited there. When it comes to compressing sort of the evidence that you provide for a state update, a simple thing you can do in some cases is signature aggregation, where you use something like BLS to compress multiple signatures together. You could, for example, use this in a DEX, in a decentralized exchange scenario, where you submit multiple orders and then an aggregate signature that is the sum total of all the signatures that prove all of the individual transactions. You can also look at sort of semi-zero knowledge proof tricks like sum proofs, where instead of providing all the balances, you provide a proof that all the balances were computed correctly. But honestly, I think at this point it's worth just looking directly into zero knowledge proofs, which just allow you to do any arbitrarily complex claim and have a very concise proof of that and submit that concise proof. Now on the other end of the spectrum, where you sort of no longer submit proofs of correctness to the system, but kind of keep even the state update proofs off-chain. You have, the simple example is state channels, where you have two parties, or at least a very limited set of parties, that send each other signed messages, and they sort of maintain the state amongst themselves. And only when they want to finalize the channel that they have, or when someone is in a dispute with the other one, would they actually submit things to the blockchain itself. So this leads to a lot of optimizations, because you don't have to submit every intermediate state update. You just have to either do the last state update or escalate whenever something goes wrong in the protocol. Now, state channels have a significant advantage in that they're usually two parties. And I know I'm right, so I know you are wrong. There is like, it's security-wise, the protocols are simple to design, because there is always, like, if one party is right, that must mean the other is wrong. Once you get to more complicated systems, and then we get to what the early iterations of Plasma were like Plasma Cash, for example, and you have multiple participants, this gets significantly more complex, where now you have like escalating games like, no, I was not wrong, he was wrong. No, he was right, the other one was wrong. And you basically have to iterate through a whole series of these operations. I'm personally not a big fan of this approach, because it means a lot of overhead if something does get wrong. It also means that you need to constantly monitor the blockchain to make sure that someone is not submitting something that is incorrect. To thwart that, they've invented slashing and watchtowers and all sorts of added-on complexity that will like do this for you. They will monitor the sidechain, the DApp for you to make sure that everything happens according to the rules, and if it doesn't, they will warn you and handle the fraud proof and the on-chain court for you. Yeah. And then on the other end of the data off-chain spectrum, we have different techniques where you can only store some sort of commitment to the data on-chain and keep most of the data off-chain. So a simple one there are Merkle trees. These are used in a lot of places already. Accumulators are sort of slightly fancier and more efficient versions of Merkle trees. But they don't do entirely the same thing. It's more of a set, whereas a Merkle tree can do an array. And there are factor commitments that add array-like functionality to the accumulators. But again, in this direction, zero knowledge proofs trump everything, because you can just implement any arbitrary data structure and do any complex commitment scheme over there, and you can run it fairly concisely. So at 0x, we pretty much concluded that, yeah, we don't want to do fraud proofs and have to deal with all the complexities of protocol design where you can unwind and revert state and all of that. No, we want to always be sure that whatever state is on-chain is entirely valid and entirely correct. We also don't want to mess with complicated commitment schemes, so we ended up with the upper right quadrant and just went full-on zero-knowledge proofs. At DEF CON 4, we got introduced to Starkware, and since then we've been working with Starkware very much on their StarkDex approach to do batch settlement using Starks. We managed to get the first Stark verifier in EVM, and funnily enough, you don't really need precompiles. You can actually do it with current EVM without any kind of hard fork necessary. Only takes 5 million gas, which is It's not cheap, but it's surprising that it works at all, to be honest. And 5 million is doable given how much of a scaling advantage it gives. It's actually less gas than if we did those transactions in the traditional way, significantly less gas. So layer 2 at 0x. There's a couple of parallel initiatives going on, so to say, that we will be rolling out over the course of this year. So the one I'm working on is the settlement layer. But in parallel to this, there is the trade execution coordinator, which is sort of a optional add-in service that will do transaction ordering for you according to different strategies. This is an alternative to what some relayers are now doing, which is a closed order book, where you kind of miss out on the liquidity sharing aspects of COX, but instead you get to do cancels off-chain. So there is a way to do this and still be able to have this open ecosystem. And that's one thing we're rolling out. Another one is that currently the sharing of order books happens through what we call the standard relayer API, which is just an HTTP JSON endpoint that the relayers need to bring up and they sort of need to poll that. We want to replace that with a peer-to-peer order book, where new people can just join by joining the network, contribute to the order book. People can plug in and get the latest state of the orders. We're working on lib peer-to-peer on this one, and we're actually extending lib peer-to-peer with decent WebRTC support. This is something that's been on their roadmap for a while, but they haven't gotten around to implement it yet, so this will be our contribution. And the cool thing about WebRTC is that this allows you to create peer-to-peer connections directly from the browser. So with this one in, we can actually have order books that go directly from someone's web tab to some other trader's web tab. And in principle, you need zero infrastructure in order to run a decentralized exchange. So all of these are right now separate initiatives that build upon our existing smart contract infrastructure. But ultimately, they all combine in a very elegant way to basically form a sidechain, where the peer-to-peer order book is not really that much different from a mempool, where the trade execution coordinator is really not that much different from a device for creating blocks of transactions, and where the Stark batching mechanism is really not much more than a block ceiling and consensus protocol. And ultimately, the consensus is hooked back into the Ethereum mainnet. So yeah, that is the sort of longer term strategy to create this sidechain. So let me talk about zero knowledge proofs for scaling. And I've actually been told that I shouldn't call it zero knowledge proof because we don't really use the zero knowledge aspects. We just use the proof aspects, which makes sense. We're not interested, we'll get into that, but we're talking here about proof protocols, and there are some optimizations you can do if you drop the zero knowledge requirement. So what is a zero knowledge proof? You have a basic function, f of x and y equals z. Now, f can be any function you want. Like, you can literally throw a piece of Python code and it can, to some extent, be implemented in a zero knowledge proof. The basic thing is that math is cheap in general, but branches and checking that some value is less than is relatively expensive, and AES is expensive, but multiplying numbers is cheap. So how things work out in practice is kind of a learning experience at this point, and the technology is not mature enough yet that you can just, like, as you would write Solidity code, do it without thinking too much. It will get there over time. It's just not there yet, performance-wise. So at this point, you need to be clever about designing your functions, but this will improve over time. Now, once you have your function that represents what you want to compute in your zero knowledge proof, you have two inputs that you can have. You have your public input. This is what you would share with the entire world, and then you have a private input. This is the zero knowledge part that you want to keep secret. And then you have an output. And the thing you're proving is that Here I give you a value for x and a value for z, and I claim that I know a value y that makes this equation true. But I'm not going to tell you this y. And the proof protocol is actually, it's the clever cryptography that allows me to convince you that I know this y without revealing it. If I just gave it to you, you can just run the computation for yourself and convince yourself that my values were correct. Now, this private input allow you to do privacy, obviously. You can do some things like, hey, here is a transaction, and I'm not going to tell you for how much, but I'm going to update the balances correctly, for example. But it's more interesting to use this for scaling, because the cool thing is that these proofs, they don't grow in the size of this private input. Like, your private input can be really, really large, but I never have to tell you the private input, so my proof can still be very small. And this is where the scaling aspects come from. In the case of a DEX scenario, the way it works is you have a function that verifies transactions and updates balances. As a public input, I take a Merkle root of the old balances. We call them faults in our design, and old trade state. We'll get into that. And as a private input, I give you the Merkle proofs that relate everyone's balances to this root, and a whole list of signed trades. So that's a lot of data I'm putting in this private chain. It's like a whole bunch of Merkle proofs for everyone's balances, all the transactions involved, all the signatures, everything. And this F function will then verify these Merkle proofs back to the root of everyone's balances, update all these balances, make sure that everyone has sufficient funds for the transactions, check the signatures, everything. And outcomes at the end, this F function computes a new Merkle tree with everyone's new updated balances, and it outputs that new Merkle tree. So again, how does my proof look now? So the proof works that here is the old Merkle root, and here is the new Merkle root, and I claim that I know all the Merkle proofs and all the transactions that make this valid. And this is where the amazing scaling comes from in zero-knowledge proofs as a layer 2 solution. So let's go a little bit more in depth in how such a state update works. So in the top row you see Ethereum blocks, and you see our little contract running in there. The contract currently has a state root that says state A. Now I submit a proof to this contract that says, hey, the old root is A and the new root is B, and here is a whole list of transactions that I'm not telling you, but there is a proof of it. So all of these different transactions you see there in gray, you don't need to submit them to the blockchain anymore. That is all sort of gas saved, and instead you just have this one concise proof. The contract sees this, the contract verifies the zero-knowledge proof, it checks that the old root is indeed A as it remembered, and then it updates it to the new root. And then you create a new proof with all the new transactions that came in and so on, and you keep updating this state root. Now, what do these state roots look like? There's actually two in our current design. The first one is the fault root, which is indexed by some fault ID, and basically in each leaf of this thing we store three values: the public key of the owner, the token ID that identifies the token that is actually stored there, and the amount of those tokens that are stored there. Next to that we have the trade root, and it contains a trade idea and a simple Boolean value telling you whether it's filled or not. So this is to prevent sort of double execution of transactions. One of the things our zero-knowledge proof verifies is to make sure that this transaction hasn't been executed before. So these transactions, there's four main transactions. There's a trade settlement, a deposit to move funds into the sidechain, a withdrawal to move funds out of the sidechain, and an escape hatch that basically guarantees security in case the whole system breaks down or any of the components become malicious. So the simplest is the trade settlement. If you're a market maker, you sign an order stating the tokens that you're willing to trade and at which price, and you put it in the peer-to-peer order book. Now the taker at some point sees this order, adds its signature, and then submits it to the sidechain operator. The operator collects many of these signed transactions and then combines them into a batch that updates the old balance root to the new balance root, and then it submits this proof to the contract, and the contract verifies it and updates the root like you just saw. So what if you want to take your tokens and put them into this sidechain? So you send your tokens to the contract. The contract now remembers in its contract storage that you made this deposit, and it fires off an event. The operator sees this event, and it includes a special deposit transaction in the batch, and also adds it to the public input. So this transaction is not hidden from the contract, it's actually included as one of the public inputs to the thing. The contract receives this proof, which has this deposit transaction as a public input, so it sees the old root, the new root, and hey, there's also a deposit transaction. So now the contract checks, do I have in my storage that this user actually deposited these funds? And it sees, yes, indeed, the user has it. So it removes this storage slot, and from now on, the funds are moved to the sidechain. And of course, if the user didn't make this deposit, the operator should not include it, and if it did include it, the proof simply gets rejected as invalid. Withdrawal is sort of the opposite thing. The user submits the signed withdrawal transaction to the operator includes it, but also includes it as a public input. Again, the contract verifies the proof and sees that, hey, there is now a publicly known withdrawal transaction, and the contract takes some of the tokens it has in its like funds and sends them back to the user that signed the withdrawal. So far, so good. But as you notice, this withdrawal requires you to deal with the operator. What if you don't trust the operator? This is where the escape hatch comes in. The user tells the contract, give me my money back. And now the contract remembers that the user said this, and again fires an event. The operator should now include a proof that, hey, this was your balance as a public input. The contract verifies this proof and sees this message and basically gives the user its entire balance back, because this proof now says this was the user's balance, they're out of the system, they want gone, so that's the end of that. However, the reason we did this escape hatch is because we don't trust the operator. So what if the operator does nothing? This is where it gets really interesting in all of these zero-knowledge proof off-chain data designs. So we have the same step. The user tells the contract, give me my money back. The contract remembers this in storage and fires an event. But now the operator does nothing. Either it just continues running the system as if nothing ever happened, or it fails to update blocks because the servers are offline or whatever. Anyway, at some point, the contract decides that, hey, it's been like more than 2 days now since this user requested their funds. You should have been dealing with this by now. I think you're a crook. So now the user can tell the contract, like, hey, here I have my own proof that this was actually my balance. Give me my money back. And the contract verifies the user's own proof and gives the user the tokens back. The reason that the contract cannot immediately accept the user's proof for this is that it conflicts with the operations that are going on. So you cannot have multiple people update the state root at the same time, because that leads to clashing state roots. So in order for this to happen, first we need to kind of dismiss the operator as non-functioning, and now we can say, okay, users are in charge. You're entirely correct, and you need the Merkle tree to do this. So what you hit on here is indeed known as the data availability problem. This is the main problem that layer 2 scaling solutions that use off-chain data deal with. Going back to the on-chain, off-chain debate, the problem with on-chain scaling is that, with storing your data on-chain, is that you can never do better than some small factor improvement over the current system, because ultimately all your transactions still have to be stored on-chain, even though you might be able to compress them to some extent by, let's say, leaving out the signatures. But yeah, in the end, you would still need to reconstruct your data. If you want any kind of better than linear scaling, you will need to have your data off-chain. But that introduces this problem where if you want to use this ultimate security escape mechanism, you will hit into this problem that, hey, some piece of information that is kept off-chain, I now need in order to unwind my position in this system. And it gets a little bit worse because usually you use Merkle trees here, and the state root just keeps updating. So if I know what my balance is right now, and I know how it traces back to the state root that is stored on-chain right now, I might wake up tomorrow and see a new state root and not know anymore how to create a Merkle proof from my balance to this new state root. So somehow, some service needs to be out there that is able to provide you with this information in a way that you can rely on this thing being there for security. This is, to a large extent, an open problem, but it is not completely bad because you can do solutions that get you most of the way there. The way we are going to solve it for our proof of concept end of this quarter is by having a committee of, let's say, around 20 data availability providers. Once a new proof is generated, the operator needs to send all the relevant data to all of these 20 committee members. Each of them signs off on this data, stating that, yes, I've received this data correctly, and I've also now shared it on, let's say, on my website, on BitTorrent, on IPFS, wherever you want it. They sign off on that fact. The operator collects these signatures, and the proof, together with these signatures, gets submitted to the smart contract, and the smart contract verified that the committee has signed off on the availability. So now your security changes from, oh, you need to trust the operator to have this data available, to you need to trust that at least one committee member has this data available, which is a significantly lesser security constraint. But ideally, you want to go even further than that. So you can add some complications in there where the contract periodically challenges committee members to reveal their data, where they have some stake in the protocol, and they will get slashed if they are not able to provide this data on demand in sufficient time, and so on. But again, open challenges. Data availability, I would say, is one of the biggest ones right now. The other one is technological maturity of zero-knowledge proofs. Snarks here have a little bit of an advantage. They've been around for longer. There is existing tooling like Socrates that give you domain-specific languages. Starks are relatively new. There are some supposed advantages in prover time, allowing you to do more complicated things. However, right now we don't have like nice programming languages for them yet. Obviously, this is something that will improve over time. But in general, the state of zero-knowledge proof is relatively fresh. This is technology that has been known for some decades now, but initially, zero-knowledge proofs were in the order of megabytes, terabytes, you name it. They were like not practically feasible. And as this technology proved over time, like they now barely hit the threshold where zero-knowledge proofs are meaningful in the context of financial transactions, where the amount of compute you need to do is very, very low and the value of a single computation is very, very high. So that's why they're finding applications here. Another thing I would like to stress is that if you use zero-knowledge proofs as a layer 2 scaling solution, you're in a much, much better position than if you use them for privacy. Because the problem is that Zcash is an example of a project that is using zero-knowledge proofs for privacy. They recently discovered, or actually during the summer, they discovered a serious flaw in the way they organize things that could potentially lead to a theft of funds. And they've been fixing this in the background, and they just published that this actually happened a month ago. And the problem is that right now, they don't even know if anyone else discovered this and exploited it, because their coin is private. They cannot see, they cannot verify that things happened correctly. If you use zero-knowledge proofs as a layer 2 scaling solution, you have a significant advantage in that you're not trying to hide what is actually going on, and people can just tally everything up and verify that everything was done correctly. So this is why I'm handing it to you. This is the perfect testing ground for zero knowledge proofs, better than the privacy stuff in my opinion. The limitations of zero knowledge proof technology at the moment mean that we don't get to do all the things that you would expect from a decentralized exchange. Like the current design, for example, as I presented it here, does not even allow you to partially fill an order. An order is either filled in full or not at all. Obviously, we want to have this as a feature before we consider this to be production grade. And there's a bunch more features, for example, cancellations that we want in there as well. Another is that, as you noticed, I was talking about a single operator here. Which is arguably a point of centralization. Now, the fact that we're using zero knowledge proofs here and not fraud proofs means that what this operator can do is limited. Basically limited to what miners can currently do, which means transaction ordering and censorship. But ideally, we would have some decentralization mechanism in here, so you can have multiple operators, so that you have some rough guarantee that, well, maybe one operator is trying to censor you, but you know what? You can always spin up your own operator and include your own transactions. Open question. Wallet support. Go into that one a little bit on the next slide, actually. But basically, zero knowledge proofs require. So right now, Ethereum uses SecP256K1, which is a particular kind of elliptic curve. Unfortunately, it is really, really hard to implement specific curves in zero knowledge proofs, and rather you would take the elliptic curve that comes naturally in the zero knowledge proof system that you're working in. Because snarks are implemented on some form of elliptic curve cryptography, and Starks similarly are implemented on finite fields, and you want to use an elliptic curve that uses the same field in order to do the math efficiently. Problem is that wallets don't support this new curve, contracts don't support this new curve. So there's some proposals out there that I've been working on for the past couple of months, hoping to get them into the next hard fork. The first one is a precompile for generic elliptic curves. So right now we basically have support. We have some sort of support for SecP256K1 through Easy Recover. We have some sort of support for the AltBN 128 curve that is used by some forms of snarks, but we don't have, like, we can keep playing this game and keep adding curves, but I would rather just have one contract where you can just enter your parameters of your curve and it will compute it for you. This will allow all sorts of DApp developers that are working on their own custom zero knowledge proof solutions to just use whatever curves works best for their system and have support in the EVM itself for verifying things like signatures, Peterson commitments, whatever. Another fun one is actually the cost of. Now, let's talk first a bit about the wallet support. Similarly to how you want to be able to verify these signatures in a contract, you actually want to be able to produce these signatures in a wallet. Right now, wallets can't do it. There is no real way to add new crypto primitives to a wallet besides sort of asking MetaMask and others to implement your custom crypto, which doesn't really scale well. So I wrote a proposal that allows you to compile your custom curve and cryptography and signing algorithm to WebAssembly, and then basically upload the WebAssembly to your to the wallet, and then the wallet will execute it in a secure way using your existing private key. So you don't have to generate new key pairs and all that. You can basically have a relatively smooth experience using zero knowledge proof based layer 2 solutions. Now, cost of transaction data versus storage. One thing I realized while working on this stuff, so Stark proofs are relatively large. They require 5 million gas, and out of that, something like 4.5 million is purely the cost of transaction data. In general, layer 2 scaling solutions, no matter which strategy you really use, they end up consuming a lot of transaction data at some point. Because if you put your data off-chain, there are points where you want to contest the result or prove something where you need to bring it back on-chain again. And usually when you do that, you even need to include a fairly large Merkle proof that attaches it back to whatever is stored on-chain. Now, you can do the math on that, and right now the cost of including a single 32-byte variable in transaction data is a little over 2,000 gas. Reading a 32-byte variable for storage is 200 gas. We're seeing a 10x differential here. It is literally cheaper to read stuff from storage than put it in transaction data. It gets even worse once you include Merkle proofs. If you want to include a Merkle proof of, let's say, depth 32, which is what we're shooting for with this system, you'll have to include 32 values. The total gas is more than 17K in this scenario. So really, everything screams at you to skip the layer 2 and just store it in storage. And this is hitting all of the layer 2 scaling solution apps out there, as far as I can tell. So yeah, there's a proposal out there to change the gas cost on when it comes to transaction data. Other proposals are kind of aiming to better support in WebAssembly for certain crypto operations, or maybe even lobby for web crypto itself to get better support for different crypto algorithms, like get it lower in the stack. Funny thing is, I've been asking around in the WebAssembly community, and basically some folks at Mozilla told me that, yeah, there was one guy from Ethereum once and we haven't heard from them since. So if we really want to use WebAssembly as a core technology in Ethereum, we really should be doing a better job representing ourselves and our needs at the WebAssembly committee. So I'm going to try and champion this proposal in there, and maybe some other ones, and just get some representation there. But this is also something we should do as a wider community. Anyway, I wanted to go to one last challenge. This is the one I wanted to save last because I think it's the most important one. This is my homework assignment, and I would say, hey, it's actually turning out to be the closing message of EthCC. We need layer 2 interoperability. The big problem with all these layer 2 scaling solutions that we're building right now is that they become little silos that force you to put your money in one specific DApp, and it locks it in that DApp and doesn't allow you to do anything other than that DApp, and it completely destroys all of the cool stuff that we have with Ethereum right now, where we have all these amazing smart contracts that build on top of each other. That 0x is a prime example of this. Like, I've seen projects use 0x in ways that I could never imagine. Just because we created this open API that has a well-defined meaning, and then people just run with it and get creative with it. If we get to layer 2 scaling in the basic way, we will lose all of this. We need to think about how can we create this sidechain in such a way that you can use multiple applications either on the same sidechain, or we can have efficient ways of transferring state between the different sidechains. No real answers here yet, but this is a discussion we should be having as a wider community. All right, that's it. Thank you all. Are there any questions?
Thanks for the great talk, Remco. I wanted to briefly ask about sort of the differences between zero access approach to this zero knowledge-based batch auction exchange and the diffusion project by Gnosis, which seems to be doing something fairly similar from my conversations with them.
So for starters, we're currently not shooting for a batch auction, but a traditional continuous limit order model. We can implement batch auctions on a different level as a trade execution coordinator. And there's also alternative strategies that we consider worthwhile, like selective delays, where cancels have a, let's say, 2-second priority over fills. The basic idea here is to create a fairer marketplace, and right now the marketplaces are to the disadvantage of market makers.
You said that you think that the future of blockchain is rather WebAssembly than EVM, yet still you're proposing new functions to EVM. So when do you think this future is going to hit us? Like, how long does it? How much time does EVM still have, in your opinion?
I don't think it's going to go away fully. So one of the cool things that happened is that basically the people that develop, let's call it Ethereum 1.x, said that, you know what, we're just going to maintain this system indefinitely and make it competitive incrementally. So this means that EVM will likely be around for a long time, although maybe in a form quite unlike it is currently, but through an incremental migration path. There is some proposals out there right now shooting for the next hard fork that add all sorts of new opcodes to the EVM that allow it to be a better target for native compilation, for example. I think EVM has a good shot of being around for a while. But I also think that EVM will sort of converge towards WebAssembly, because WebAssembly is sort of already doing more or less the optimal thing here.
For the interoperability part, would you prefer Polkadot parachains or Cosmos, or what kind of model would you?
Those are all layer 1 solutions. I'm talking about layer 2.
Ah, right. Okay.
Last question.
Are you satisfied with Alt-BN 128, the security of that for the zero-knowledge proofs that you're thinking of including in 0x?
Which ones?
Alt-BN 128, the pairing curve.
We're not using that one. We're using Starks. Starkware is this company.
Oh, you're, okay.
Starkware is this company in Israel founded by Eli Ben Sasson and Ale, who were some of the pioneers of Snarks in the first place, and they now, or relatively recently, came up with a better scheme that doesn't require pairing cryptography at all. It has actually fairly simple mathematical foundations.
Yeah, but there's no precompiles for that. Are you waiting for precompiles, or?
Like I said, we can already do it in existing EVM. We don't need any precompile. We have implemented the whole thing in EVM assembly and got it to the point where it can run within, let's say, 6 million gas.
But isn't the block limit like 4 million gas?
It's 8 million.
8 million? Okay.
If we get these proposals in that change the cost of transaction data, this will change, because it's actually something like 1 million worth of compute, and that's not even optimized yet. If you look at Snark-based zero-knowledge proofs that have some amount of data input in it, they also cost 1 million gas. So it's actually quite competitive already if you look at it that way.
Last question.